Let us try to understand what are the distinct characteristics of the data centers in terms of how they differ from the traditional internet or the networks. First, we can see that this data center network spans a large set of distinct devices, but they are all under a single administrative domain. Unlike the internet, where you have lots of networks that are managed by different organizations and different people, here such a large scale network is all under a single administration. And this gives us flexibility in one way, where we can change or scale the endpoints as necessary. That means the way we interconnect, the way we build the requirements for topologies to be set up, the way we want to change any of the components or accessories within the network, all are at our will. And second, it also gives us an additional flexibility in saying that whatever the way we want to transact the traffic within such an internet would necessarily be at our will. That means we need not have to enforce ourselves to be compatible with the outside world or follow any standards, and we can easily adapt or change any of the communication protocols that we want to build within such a networking domain. Second, when we look at the services that these data centers provide, most of the web traffics, the search queries, all of them, we also see that inherently whenever we are trying to build such a network and want to provide fast responses, they need to have very small round trip times, at least within the data center. Any connection over the internet, we cannot have any control over the latency. But when we look at this network that we build within a data center, any communication within that would have very small round trip times, typically of the orders of just around tens of microseconds or even smaller. And also, we have flexibility to build these switches and routers that we would want to plug to facilitate connection amongst different servers. And we can build any kinds of topologies that suit better for the kind of workloads that we would want to support in a data center. And typically, we would multipaths amongst the different servers so that even if one of the failures occur for one of the devices or links, you have other paths to reach. And also, the aspect with switches and routers is how deep or how shallow the buffers can be. And if we want to characterize them to have a low latency communications, we would want to build very shallow buffers so that they are just enough to accommodate any bursts, but not long enough, leading to a lot of queuing latency. And this latency has been very critical, especially with network as a backplane, to facilitate large-scale parallel computations. Hence, this aspect of how you buffer the switches, how you want to build the multiple paths, and ensure that you are able to have latency-sensitive applications to be able to communicate within such a data center become a critical aspect. And what all of this provides us is a distinct opportunity in terms of how we can redesign the L2, L3, and L4 protocols, or even the layering where we want to bypass or adapt, just as in within the data center network's communication. But when it comes to the communication outside of the data centers or through over the internet, we would have to adapt to the standards that would ensure that we are able to communicate outside. So if we peek further, what we are looking at in this figure as a data center network, we can build the way we communicate from the internet with the servers that we host in our data centers, and weave what we call as a fabric or a network interconnect that ensures how we want the communication, latency, communication, link resiliency, multiples of the link multipaths, all of these characteristics through this fabric. So that means we could build many different kinds of topologies, ensure that we can have different servers that can be reached through different paths, through different network elements. And we can also have different kinds of network elements, not just that they are Ethernet based. They could also be fiber optics, the optical communication channels being set up for communication. So all of this that we can try to achieve what we say as a massive bandwidth that we want to offer for both the communications that happen within the data center and for the communications that happen within and outside of the data center. And we will learn about what we mean by bisection bandwidth, but in short, this basically refers to the bandwidth, the maximum bandwidth that can be offered by the given network. And Further, when we want to support ultra-low latency applications, the characteristics of at each switch or a router, how do we want to ensure that we can schedule the packets? What are the different means to schedule the packets? We can try to provide those updates, whether we want to have a centralized or distributed routing, what is the means to control the rate for each of the packets. All of these aspects can be plugged in the way that we would want to see that works better for the data centers. And also, the other aspect is with respect to the resource management, wherein when these data centers are going to be leased to multiple of the tenants to host their services, each may have different requirements. So to meet their requirements, how do you want to manage specific devices? How do you want to ensure that when multiple of the tenants are going to be sharing the same infrastructure, how do you guarantee the performance isolation? All of these become critical aspects in terms of networking design. So the earlier aspects that we learned about the network virtualization and how SDN can ensure that you can route the packets distinctly for different flows, how the NFV can ensure that you can run different network applications that can be scaled to meet any scheduling aspects for the network flows. All of these become handy to be plugged for these data center networks. And moreover, also when we want to build these servers that are going to serve lots of traffic, we want to ensure that we can do in-network computing, and that is possible through the upgradation to the next generation hardware by using the programmable NICs and switches, or the use of better alternatives for remote DMA, so that the communications can work in a much more faster fashion. And all of these is possible because we have the entire control over the networks. So the other side of it would be to think and see how it comes in terms of the workload. So data centers, typically what we see is they run two kinds of applications. One we call as the north-south traffic. That's the typical traffic where an end user would connect with one of the servers, web servers, or etc. that's running within a data center. So this is typically the traffic that is carried over the internet, and then you would access the resources within the data center. In the earlier case, we saw about a Bing search. So and when a user makes a search or a query, this query is facilitated to the data center, and this constitutes the north-south traffic. And the other traffic is what we call as the east-west traffic, wherein we saw that once a query lands into the main server, it disaggregated and distributed it across worker nodes that are present within the data center network. So the traffic then spread within the data center. So the kind of a traffic where the MapReduce or web indexing, etc. take place, or even like when you want to migrate a VM from one node to the other node within a data center, all of these result in the traffic that is moving laterally within the data center. And such a traffic is what we call as the east-west traffic. And when the data centers were characterized, it was seen that this east-west traffic constitutes to more than 80% of the total network traffic that is carried, while the north-south constitutes to around less than 20% of the traffic that the entire data center carries. What this means is one query of X kilobytes would result in 4 to 5X kilobytes or megabytes of data that is being carried within the data center to facilitate the user's request. And there is also additional information or bookkeeping or management that happens within the data center, and all of that constitutes to this east-west traffic. So now what that means is when we want to be throughput and latency sensitive, we want to take into consideration what aspects of north-south traffic in terms of latency sensitivity we should be worried about, and what aspects of latency sensitivity for these east-west traffic we should be worried about. And throughput in terms of if we are trying to do a migration and doing lots of data that's like several gigabits of data that's being transferred, then we also need to be throughput sensitive in terms of how the traffic moves across the east-west. Hence, all of these characteristics need to be understood well for designing such data centers. And often that these workloads are also unpredictable. What this means is that the amount of data, like when we see a typical user pattern, like maybe early in the mornings, you may be looking up for news over some specific sites, and maybe during the evenings, You may be looking for some video streamings or gaming or kind of refreshment or entertainment activities. And the way you would access different resources is going to change over time. And if there is a cricket match or something going on, maybe you are hooked in to get some specific updates in a given day, or while a football match is going on, maybe you're looking for some other kind of a data. And likewise, and any events that are happening, maybe you're looking for specific such data. So all of these mean that there would be spike for the demands of new services over a given period of time. And these demands are maybe expected, maybe unexpected, as if some disaster happens and you are looking for the updates on such disasters. And if there is Olympics or some games that's happening, and these events may not be periodic, and they may be more sporadic in nature, and that would affect how the data centers have to serve different traffic. And all of this also means that when we want to build a network, we don't have any assumptions about what kind of traffic we have to be dealing with. And this means that we could also be dealing with some unprecedented aspects of traffic that we will have to absorb. That means the resources that we may have may see some peak usage, while at times they may see no usage at all. So all of these need to be accommodated when we want to build the data center networks. Further, when we are speaking about a lot of these server machines, any of the servers, especially when we are speaking in the volumes of hundreds of thousands of server machines that are hosted in a data center, failure of one or two instances becomes very normal. And this can be like a routine in terms of every alternate day, you may see 5 to 10 different devices that may fail. So that means we should be able to also absorb such failures and ensure that we are able to build the networks that are going to be resilient to such failures. And also the traffic metrics in such scenarios would see that whatever the data that used to go to one particular server, which may be having failures, would now need to be migrated to another instance. And also, when we have these devices, lots of them, it's always that we will end up having to manage those devices and update. So there will also be a known downtime that you would have to manage with respect to when the devices are going to be upgraded or patched. So maybe it's software or hardware upgrades that you would want to do. So all of these would require that this traffic matrix may keep changing between different servers at different points in time. So when we want to build such networks, we want to be considering all of these characteristics to ensure that our data center architecture is able to absorb these characteristics. And the most crucial part when it comes to the data centers, like in all of these cases where the services are up and running, when we want to maximize the utilization, or when the services are down and you want to ensure that the data is going to be worked out from some other location, load balancing within data center becomes a very crucial aspect. And especially when it comes to the application layer, where we are trying to ensure that the applications don't see differences in the time of service requests the way they're honored, or any failures, then we need to ensure that a proper load balancing mechanism is set. And typically, when we look at the north-south traffic, the data that comes in through the internet all the way to the border router or the core routers and then through the access routers, we want to ensure that we run through the load balancers. And these load balancers could be the dedicated hardware like middle boxes, or could be the NFV, the virtualized instances that we may be running in any of the server racks, or even hosted on top of the switches in programmable networks, or even it could be run as a part of an SDN control. So all of this different means where we can run the load balancer, but our goal now is to ensure that whatever the traffic that is coming is getting load balanced within any of these server racks, wherever the server would be located within this network. And once the requests are being load balanced, we would also see that the workloads could be directed or redirected within the data center, meaning one of the servers could point to other server to facilitate the communication, get the information back, and then send to the communicate back the information to the external client. So all of these characteristics of how we want to redirect, how we want to manage, and maybe we will have multiple of the directions that may also happen, all of this can be managed transparently within the data center networks. Hence, how we better load balance, what are the means to load balance, what are the means to disaggregate the requests, all of these are critical aspects in data centers. Further, like I said, like the data centers have a rich interconnection amongst the switches and racks. So any traffic that's entering, you will have multiple of the paths through which the requests can be made to reach a particular server. So if we consider any of the devices here, if they want to communicate to any of the devices in any of the other racks, and the most obvious path, if we consider the communications between these two ends, you have basically the top of the rack going through this device, going all the way to the tier 2 switch, and from tier 2 switch, you can see that we have 4 of these links, which allow us to either go through this device or go through this device or through this device. And then once we have gone to this particular device, then we may see that we can go through this and then eventually reach this device and then reach out here. Or even we can reach out through this and directly over to the switch and reach out here. So we can see that we are having lots of paths to make sure that we can reach between two given source and destination points. And these multiple routing paths ensure that we have redundancy of paths from between the two ends. And this redundancy helps in building better reliable communication. Meaning, if we had any of this device fail, let's say this device failed, in that instance, we have to choose an alternate path from this device all the way going to this new device, and then we can have this. Or if even this device fails, we still have another path that would allow us to communicate. So we are able to handle multiple of such failures. And this means that whenever we want to build the topologies for such data centers, we want to ensure that we are able to accommodate such failures. So to put it, we may want to build what we call as distinct multiple routing paths, wherein the overlap is as minimal as possible. So what we saw earlier, we had the same top of the rack going through different tier 2 switches in the same way. Like if any of these tier 2 or tier 1 switches fail, we would want to have alternate tier 2, tier 1 switch path. And even if any of the other tier 2 or tier 1 switch path, tier switch in the path fail, we would want to have an alternate again to facilitate that we are able to communicate. So this kind of disjoint paths is more critical to ensure that we are able to facilitate the multipath communications, even in the events of multiple device failures or multiple link failures. And that's a very crucial aspect in building the data center topologies. So having worked out the key characteristics and what we are trying to see, if we want to summarize the key networking objectives when we want to build the data centers, is foremost is a high uniform capacity. So because we are talking about lots of servers that are going to communicate and work together, we want to ensure that the two servers are going to have very high bandwidth between the two in terms of network capacity. And it shouldn't matter where they are located. Maybe they are on the same rack, they are across different racks, across different pods. All of these should be immaterial, and we should be able to ensure that they still have very high capacity. And this would ensure that we will have the communications that can happen at a line rate, meaning if I have a 10 gigabit NIC for all the devices, the two of the servers should be able to communicate at 10 gigabits per second. And second, because these data centers are going to be hosted services from multiple of the tenants, we also want to ensure that there is a performance isolation. And this, from the networking standpoint, what it means is traffic from one tenant should not impact the other tenants. So there should be complete isolation between the traffic metrics that goes within the data center, across data centers for different tenants. Second, there should never be a single point of failure. Like any device that would fail should not result in the halt of the services. So you want to avoid such single point of failures and ensure that the oversubscription of links should not be done as much as possible. And when we oversubscribe, this is where the different workloads may impede the way the traffic would flow from one end of the device to the other. And hence, we would want to avoid both single point of failure and oversubscription of the links when we want to build the network topologies. Third, whenever we are talking about a span of thousands of devices, we also have to keep in view how we better manage these devices. So keeping these devices at a layer 2 with a plug and play concept where you don't have to hardwire any of the IP addresses, or ensure that you don't have to reprogram or recheck with respect to what other devices have, and then try to bring these concepts of how to address, how to build the information have to be considered. But as we said, we still need the IP addressing if we have to host the servers and make them run. So thinking in terms of a flat addressing, like what a unique address L2 gives, such as semantics, would be more easier. So if I say that there is a rack and this rack hosts particular addresses, we could define a semantics of how to break this address space and ensure that IP addresses can be provided accordingly. But that is not just sufficient, because we said if there are devices, there are servers that we are going to move, the location of one server that is running on one physical rack might be moved to another in a different point of time. So also this address transparency in a way becomes more crucial when we want to build this semantics of services that are accessible across data center in any of the racks. And this service configuration that we want to see is identical to LAN, because when we have a device that's connected to a LAN, no matter where in the LAN you are going to connect, you are going to have the same IP. So likewise, we want to ensure that these services that are going to be run in a data center act as if they are under a single LAN. And also, whatever the mechanisms that we want to bring should not hinder in any way the legacy applications that would run. And what we are specifically trying to point here is, when you have a very small LAN, broadcast is okay. But when we think of data center as a LAN of hundreds of thousands of devices, broadcast can be expensive. But that shouldn't mean that these legacy applications which rely on broadcast be stopped. What this means is, in a way, the way we want to multicast or broadcast within a data center has to be in much more contained and controlled manner. And again, this is where a software-defined network, in a way where we centralize the information and percolate the updates wherever necessary in terms of how we want to manage, all of this becomes very handy. And that's where, well, when you look at the Google data centers, starting from the days of B4 to the Jupyter approach of how they have managed the B4 way to interconnect the WANs and manage different data centers. And likewise in the Facebook's architecture that we'll see, they have tried to use the concepts of SDN to better manage and address the programmability of these networking devices. And last but not the least is this manner in which we want to build the data centers also need to ensure that they are cost effective and power efficient. That means we want to, as much as possible, build infrastructure that is affordable, and then ensure that the carbon footprint of these devices and the way we want to regulate these devices always results in lower power consumption and heat emission, in a way that this is a sustainable design. So all of these characteristics need to be taken into account in building such data centers. And there was a good amount of research that's been done in this aspect starting from the early 90s, and it has seen a lot of evolutions in terms of how the data center networks have evolved. But we will try to look in terms of trying to address and understand what goes behind, and at least to the formal way of addressing in understanding how we should be designing such data center networks. And the first of the kinds that we should be learning is is most commonly followed approach is what we call as a Fattree topology. So we looked earlier in this without giving it a proper naming, but in terms of addressing how the hierarchy is set up. But this Fattree topology leverages the way we built that hierarchy and tries to add specific points about how this hierarchy should be specifically built in terms of what interconnects at different tiers need to be done. And the idea here is that we want to improve the reliability, and this is possible through redundant paths, as we saw. And we want to ensure that the bandwidth or the network capacity between any of the communications across any of these devices that are sitting in any of the racks should be either similar or same as much as possible. And to do this, the very simple idea is, if we consider the edges at a level k, they should have at least 2 or more times the capacity at the edges that are at level k plus 1. I mean, as we go lower, the levels keep on increasing, and the root being the topmost level. So the capacity should be increased between, like if I had this communication between the server and top of the racks all on 1 gigabit links. This considering the level 2. Then as I go up to level 1 at the tier 2 switches, I want to at least double this 2 gigabits or 4 gigabits so that it's greater than twice. And likewise, when I go to this level 0, in this case at the tier, I want to have at least around 4 to 8 gigabits per second. And this is the idea of trying to say that we are able to facilitate the connections that have multiple, that are able to scale and facilitate given network capacity accordingly at each of the layers. And this design principle is what comes up in the Fattree topology. And what it really means is whenever you're trying to build this network, your links would have increasing capacity as you go towards the root. And this means, like what we said, this is 1 gig, then I want this to be 4. If this is 1, I want this to be 4, and I want this to be 8, so that any of the communications will see that end-to-end you're going to have the same capacity. So if 2 of these devices are connecting, they have a net capacity of 1 gigabits per second. Now, if any of these devices want to communicate over this, then both of these devices would go. So that means if I keep it at 2 gigabits per second, I'm ensuring the same capacity that I had ensured the connection between these two to any of these two. So they will still have 1 gigabit per link, even if all the connections are running simultaneously. And when I have this instead of 8 just as 4, then I'm ensuring that any of the connections that happen between any of these devices, you can have 4 of these to communicate together, all may still get 1 Gbps bandwidth. And likewise in the scales of 1:2:4, if you scale up the bandwidths, it would ensure that you are able to meet the bandwidth requirements, the network capacity for each of the connections to be same regardless of where they are situated. And in this aspect, we would also want to look at what we mean by bisection bandwidth. And like I said, this is the max bandwidth that you can afford within a given data center network. And the way to put it is, if I divide this network, like bisection is basically to cut the network into 2 equal halves, and how you want to cut is basically the minimum number of links that you would cut to ensure that the network is partitioned. And in this case, if I see from the top, if I have to partition this, basically I would have to cut at this layer to say that I can partition this into 2 equal halves. And when I do that, whatever the links that I cut in this path, and if I aggregate all the capacities of the links, then it gives me that is exactly the bisection bandwidth that I will be left with when I bisect such a network. And our job is that when we try to do this, you can see that I can bisect at this path by just cutting these links, and I can bisect the tree at this path by cutting these links and these links. So likewise, we are able to partition. And when I bisect at this level, I can basically cut off all of these links. So the number of links that I really cut, and if you aggregate the bandwidth of such links that you would have to cut, that gives us the bisection bandwidth. And our goal here is to ensure that each layer has the same aggregate bandwidth. And as a means, what this Fattree topology tries to provide is, when we want to connect this, we basically think of these as the switches with K ports, wherein the number of incoming and outgoing connections are defined to be K for each of the level. So if we consider just this, and if we mark these devices to be 1, 2, 3, 4, 5, 6, 7, 8, this switch, these 2 devices are connected to this switch. So this switch has 2 of the links that are connected, and this is going to have 2 more links upwards if it has to facilitate the same. Consider this fat pipe as 2 distinct connections that are being made. So that means at this switch here, we have K equal to 4. And likewise for this, K equal to 4. And for this, the number of ports that you would see, that would go up. So how we want to build this Fattree is to make sure that we are able to scale out in terms of the number of servers that we want to support. And we should not have a means where we say, okay, this switch has K port requirement while this switch has 2K port requirement, and so on. We want to also make this uniform in a way that all the switches that are going to plug should be K ports, that is a switch with 24 ports, 48 ports, 16 ports, or 32 ports, but not the case where one of the switch is 16 port, other of the switch is 32 port, and keep adding in this heterogeneity. And why we want to have this uniformity is also to ensure that the link paths that we want to build from one to the other, the management aspect that we want to do in terms of how we configure these devices, all can be uniform.